So yeah, so my name is Yukun Huang. I'm currently a postdoc fellow at NAOJ. So today I like to share some of my recent research on the formation of the outer solar system, and also give you an update on like what our current understanding of the outer solar system looks like. Because just recently, just last month in July, a new object belongs to this group called Cenoids was discovered by Subaru Telescope. So this object called 2023 KQ14. Okay, so its orbit is really hard to explain, and we need some like new hypothesis. It may foretelling something new about the history of the outer solar system. So today, I'm very happy and very honored to have this opportunity to share my research with all of you. So yeah, so let's just jump into today's topic. So we will focus on our solar system. You know, we all know that our solar system is made of 4 terrestrial planets and 4 gas giant planets, right? Besides the 8 planets, we also have thousands or even millions of small bodies. And these small bodies are actually the key to understanding the formation history or the evolution, the dynamical evolution history of the solar system, right? So it's kind of like you're working in a desert, and all the traces you leave are like made of small sand. So it's the same analogy. So you use small body to understand the evolution or migration of the planets. So far, we have discovered 4 major small body reservoirs. So the most famous one is, of course, the asteroid belt. It's actually not very clear on in this plot. It's like actually inside the orbit of Jupiter. So we have currently discovered 1.2 million asteroids, and their total mass is like 3% of moon mass. Okay, and outside the orbit of Mars, there are also Jovian Trojan. So Trojan is the name we gave to the asteroid who share the orbit with Jupiter. Okay, so they basically they orbit the sun on the same orbit as Jupiter, but they're positioned like minus and plus 60 degrees. So that's why we gave them this special name Trojan. Okay, so far we discovered 10,000 Jupiter Trojan, and the total mass is like 0.08% lunar mass. Okay, and let's look further beyond. Let's look at the orbit beyond Neptune. Okay, so this is Neptune's orbit, and you can look at all the red dots here. So they are either called trans-Neptunian objects or TNOs, or maybe more famously known as the Kuiper Belt. Okay, so now we have discovered 4,000 Kuiper Belt objects or trans-Neptunian objects, and we estimate that their total mass is 5% Earth mass. And you can already see that there's a huge difference between the total mass of the trans-Neptunian objects and the asteroid belt. So actually, even though we discovered like 1.2 million asteroids, but the real mass, the real thing that matters is in the outer solar system. So we have so many small bodies or asteroids to discover. Okay, and even beyond trans-Neptunian objects, we also hypothesize there could be an Oort cloud. So Oort cloud is kind of like this cloud-shaped zone that hosts long-period comet. We believe the long-period comets, such as the last year, there was a famous one called Tsinghua Atlas, right? So they most likely come from the Oort cloud. And the total mass of the Oort cloud is even larger than TNO, than the Kuiper Belt. Okay, so today I would like to focus on this region, the TNO or the Kuiper Belt. So just to remind you, they have their orbit just outside the orbit of Neptune. Okay, so because I'm a celestial dynamicists, planetary dynamicists. So we often do not do research using this map. Okay, we want to convert everything into a more convenient space. So in this case, a more convenient space is defined as follows. Okay, so please bear with me. So there's a little bit like geometry you need to learn. So we know that from Kepler, so Kepler from 400 years ago figured out the Kepler's 3 laws of planetary motion. The first law says a planet orbits the sun in elliptic orbit, right? And the sun is on one of its focuses. Okay, so that's Kepler's law. So we know that also applies to asteroids. So we know that asteroids also orbit the sun on elliptic orbit. And this is a diagram of an elliptic orbit. And we call the closest approach, okay, the closest distance between the asteroid and the sun, the perihelion. So the perihelion is often denoted with small q, okay? So that's the closest approach. And we call the furthest approach the aphelion, okay? And we call the this length, so which basically denotes the size of the eclipse, the semi-major axis. So this is the semi-major axis, and that's the perihelion. So more conveniently, we tend to like redraw everything, redraw all the small body into this kind of diagram. So the x-axis is the semi-major axis, which denotes how big the orbit is. And the y-axis is the perihelion distance, which denotes where the closest approach of the orbit is, right? And you can see that Neptune is still right here. Neptune has a circular orbit. A circular orbit has perihelion equal to its semi-major axis. So that's why on this plot it's located at 30, 30, because it has a circular orbit. And everything here doesn't have, they don't have a circular orbit. Their orbit looks more like this, looks more like an ellipsis. And to better understand them, we need to classify them, right? But I don't want to go too deep into the detail of how to classify them. But as you can see that you can classify, you can basically like color code them based on their dynamical class. Okay, but it looks like a giant mess. How do we create this giant mess, which is a reality in our today's solar system? That's a big question that bothers astronomers for like more than 20 years. And we finally have some clues. So one of the model that explain the formation, this giant mess, the formation of the outer solar system, is what known as the Nice model. Okay, so Nice is a very famous observatory in France. So many great astronomers or theorists work there. So in like sorry, that's not 2021. That should be 2004. So in 2004, a bunch of astronomers in Nice Observatory, they come up with a model that try to explain the formation of the outer solar system. And the model basically looks like this. So here we have the Sun, we have Jupiter, Saturn, Uranus, and Neptune, okay? And outside the orbit of Neptune, we also have a ring of what we call the planetesimals. So planetesimals are basically just the progenitor of asteroids, right? So these are the asteroids we want to explain, and these are the 4 giant planets we know. So now let's play this movie. I think I can just, yeah. So you can see that the planets will interact with the small bodies, the green particles, dynamically. At some point, okay, so yeah, please wait for it. This animation is a little bit long. So at some point, something called planetary instability will happen. Okay, so this instability will basically bring chaos to our solar system. And this chaos is exactly what create today's Kuiper Belt. Yeah, just like that. So this is just one model called the Nice model, but with with some recent development, this kind of model has been rephrased or like re-summarized as rebranded as a planet instability model. So in this kind of model, there's always some kind of instability where, the outer giant planets like Neptune and Uranus like enter into the green zone, the green zone occupied by asteroid. And they scatter because they're so massive and asteroids are so small. They tend to like scatter the asteroid around. And the end result is something looks like this, right? Because, if something formed initially, if they never get perturbed, they tend to have circular orbit. But if they're getting perturbed, they tend to like become a giant mess that looks like elliptic orbits, right? So we can this is another diagram basically showing you the same story, right? We have the 4 giant planets, and before the planetary instability, there are a bunch of small bodies near Neptune, near Uranus. And then after the migration, after the planetary instability, Neptune migrate from its primordial location to its current location at 30 AU. And then in the process, 99% of asteroids were ejected. Okay, they were gone. They become interstellar objects made by our solar system. We have also recently discovered the 3rd interstellar object. So this process happened in our solar system may also happen in other planetary systems. So that's very interesting. Okay, so 99% of planetesimal got ejected. And the residue is what we call the hot population of the Kuiper Belt, or the hot population of the trans-Neptunian objects. So this is one of the most popular hypotheses in explaining the chaotic, the excited nature of the Kuiper Belt. Okay, so yeah, so do you have any question? I don't wanna, yeah, go ahead.
I missed why they're called hot and they're called cold.
Yeah, so yeah, this is probably not really relevant, but yeah, I can go deeper. So cold population are TNOs formed in situ. So they formed locally there, and they're unperturbed by the giant planets. However, hot population are not formed there. They form closer in, maybe 20 AU or something, and then through this planetary instability, they got implanted. They migrated to those locations. Yeah, this is like indigenous people, and this is like migrated people. Yeah, yeah. Okay. So any other questions? Take us.
By excited, you mean the orbit is elliptical?
Yeah, so by excited, I mean their orbit is no longer circular, it's elliptic. And they also have some orbit inclination. Okay, so let's move to the next slides. Okay, so yeah, this model is great. It explains a lot of stuff, but there's one population that it doesn't explain, which is the senoid population. So what are senoids? So senoids is just a made-up term to call Sedna-like object. Okay, so Sedna is this guy. It was discovered in 2004 by Mike Brown. So Mike Brown is the infamous or famous Pluto killer. So because of his discovery, Pluto got like demoted from a planet to a dwarf planet, and he's very proud of it. But he also discovered Sedna in 2004, right? And Sedna, as you can see, okay, so the x-axis is the semi-major axis, denote how large the orbit is, right? And the y-axis is the closest distance towards the sun. And you can see Sedna is right here. Its semi-major axis is 500 AU. It's so large, 20 times larger than the orbit of Neptune. And its perihelion is at what, 75 AU, which is 2 times the orbit of Neptune. So in other words, Sedna almost fell feel nothing. It never feel. It doesn't really feel the perturbation from Neptune, right? Because Neptune is at 30, whereas Senna's orbit is very large. And besides Senna, we also discovered a bunch of other Senna-like objects, including now we have 4, including 2012 VP113, Lele. I don't know how to pronounce this his full name. It's a Hawaii name, and also 2023 KQ14, which is nicknamed Ammonite, discovered by Subaru Telescope. So 2 out of 4 senoids we know are discovered by Subaru Telescope. That really demonstrates how powerful this telescope is. Okay, so what can we learn from this population, right? So we know that they have really large perihelion. Like I said, that means their orbit is very far away from the gravitational influence of Neptune, which means their orbit is much, much more stable than these guys out here, okay? And there is also a very huge observation bias. So what is an observation bias? We know that Kepler's second law said the larger the orbit is, the longer the orbital period is, right? So an orbit like Senna, so Senna will basically spend most of its time at a few hundred AU, at a few thousand AU, without even getting close to the sun. And at that distance, you cannot, you just, with any telescope, even with JWST, you cannot discover Senna. So you can only discover Senna when Senna is near its perihelion. And you only have a very tiny window to discover objects like Senna and other senoids. So there is a huge observation bias that penalizes objects with large A and perihelion, okay? So because of that, although we only discover 4 objects here and maybe thousands of objects over here in the traditional Kuiper Belt, but the reality is senoids actually outnumber the Kuiper Belt objects by an order of magnitude. Okay, it's roughly 10 times more massive than the black dots over there, which is the traditional Kuiper Belt. Yeah, so we need to take into account that. And I like to highlight this senoid, Ammonite, which is a nickname, recently discovered by using the Subaru Telescope, and NAOJ's public outreach office made a really, really nice video showing you how large their orbit is. So you can see, okay. Yeah, so these 4 are the 4 senoids we currently know, okay. And I would like to replay this movie just for you to see. Okay, so that's the red orbit is the newly discovered senoids, KQ14, and the other 3s are existing one. Okay, let's play that again. You can see that. Okay, this is Neptune's orbit. Yeah, this is Neptune's orbit. And you can see that their orbit is very far away from Neptune's orbit, right? So that's why they're different. They're unlike other Kuiper Belt objects. Okay. So, and this is a GIF showing you the discovery of this new objects by my colleague at Taiwan. So can you see it? It's very hard to see, right? Without this green circle, I guess probably most of you will just miss it. But this is the actual astronomical data we're working with. So we have to find the moving objects from this messy and very noisy data. And that's how we learn more, we advance our knowledge of the outer solar system. And this object is discovered by the fossil collaboration, which stands for Formation of the Outer Solar System, and IC Legacy, so which is a collaboration led by Japanese astronomer, and a lot of East Asia astronomers are also part of it. Okay, so what's how bizarre are senoids? Why can't we just explain them with the NIS model, which I just showed, which explain like 99% of the existing Kuiper Belt. Well, I just said like to explain in the NIS model, you have a sun over here, and Neptune initially was not formed at 30 AU. Neptune was formed further in, probably at 20 AU or something. So it needs to migrate into this planetesimal disk, which is the green dots I showed in an early movie. Okay, as soon as it migrates into this disk, it starts to scatter stuff, right? But because Neptune is at 30 AU, it scatters stuff closer to its own orbit. That makes sense, right? If you throw a boomerang, right, it will come back to you. But it's hard to like throw a boomerang, and when it comes back, it's like further, like 2 times away from you. Maybe that's not a good analogy, but you get my point. So yeah, my point is it's just very hard to like scatter a orbit out of its own orbital range. So let's say in this case, the perihelion of this orbit is close to 30 AU. That's because that's where Neptune is, but it's very hard to scatter an orbit to, let's say, Q equal to 80 AU. So in other words, we need some additional perturbation to make it happen, right? We need more than the 4 gas giant planets. So what we need exactly? Okay, so there are many different hypotheses in terms of explaining the formation of the outer solar system. So one hypothesis is called a stellar flyby. Okay, in this hypothesis, here I have a star. So this is the sun. This is the star, not from our solar system, like from somewhere else, another passing star. So it's like a passenger. So this star will like basically travel through this disk made of small bodies, and you can see its gravitational influence here. Okay, so it goes in, it goes out. It actually kidnapped a bunch of our solar system's citizens. You can see, yeah, some of them got kidnapped, but a lot of them got placed into another orbit, and you can see that you can actually produce their high perihelion structure with a passing star, with a basically a kidnapper. Right? We can watch this movie again. So it goes in and goes out, and it creates the structure in the AQ space, and that's all we need. Okay, so that's one hypothesis. Okay, the second hypothesis is called Planet 9. So how many of you heard of Planet 9? Man. Oh, that's a lot of them. So I'm in the right audience. So Planet 9 is a hypothesis originally proposed by Bertigan and Brown. So there are 2 professors at Caltech back in 2016. So it was first proposed to explain the so-called current orbital alignment around senoids and extreme TNO. Okay, so what is current orbital alignment? It's very obvious. So it's like you can see it visually. So these are the orbits, the elliptic orbit. You can see that it's not like isotropic, or it's not like distributed homogeneously, uniformly around every angle. So there's definitely some orientation, some preferred orientation. So they call this the orbital alignment or orbital clustering. And to explain this kind of orbital alignment, so why the orbits are all like this but not like this, they invoked a Planet 9. So this is so I don't think Planet 9's orbit is shown here yet, but Planet 9's orbit would be something like this. However, there are some recent study on the validity of this alignment, which could be due to some observation bias. So the fundamental evidence for Planet 9 has been recently questioned. Also, they spend a lot of effort and telescope time. So Bertigan and Brown, they spend a lot of effort trying to find this planet, but still they got nothing. So they have searched for like almost 10 years, but yeah, no result. So people start to doubt the validity of this planet. Does Planet 9 really exist? And we also discovered a Senoid like 2023 QQ14 whose orbit is like this way. So it doesn't align with the so-called orbital alignment, so which is a counter evidence for Planet 9. So I would say, like right now, Planet 9, Planet 9 as a hypothesis seems to be declining because a lot of evidence show that this is either just an observation bias or you can actually found non-aligned senoids and TNO that's inconsistent with Planet 9 hypothesis. Okay, so I personally don't really think there is enough data to support Planet 9 anymore, but maybe that's still under debate, okay? So, so that's like two hypotheses. One is a passing star. One is an existing planet in the outer solar system. And what kind of other idea we can have? Okay, we can first look at some solid evidence, okay? So we know that the 4 giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, they all have roughly 10 Earth mass giant planet core. So their core has enough like solid material up to 10 Earth mass, okay? And we also know super Earth are very common in exoplanets. This has been very well understood through recent surveys such as Kepler. So it has shown the Kepler telescope, not Kepler the astronomer, has shown that super Earth are like the most frequent, the most common exoplanet in outer solar system. And another evidence come from microlensing survey. Okay, so what is microlensing? That's another story, but a long story short, microlensing is something like, okay, so this is a star, and if something dark pass through the star, like pass in front of the star, it will cause the light will burn around the dark object. Let's say the dark object. So my hand is kind of like a dark object, like a free floating planet, and this is a star. Okay, so when the dark object pass in front of the star, the light of the star will get amplified due to the microlensing. So microlensing is due to Einstein's general relativity. Okay, so it works like a lens. So this free floating planet will work like a lens, and you know, like when there's a lens, the light will tend to like get focused or get dispersed, right? So this is called like microlensing. So in microlensing survey, people, they just stare at a lot of stars for a very, very long time, like for more than 10 years, and they detect this kind of like spike in the data. And once they detect the spike, if everything checks out, they say, oh wait, we discover a free floating planet, right? So, and you can actually work out what kind of number, what kind of free floating density you need to explain the microlensing survey, microlensing data. And the recent data shows you probably need roughly 20 Earth mass planet per star. Okay, this is per star, which means like every star corresponds to 20 free floating Earth mass planet in the galaxy. You need that much to explain their observation. This comes from also a Japanese astronomer in work at Osaka University, Sumi et al. So it's their 2023 result, but it has huge error bar, and this will be confirmed with the Roman Space Telescope. But if this is true, that could imply that ejecting Earth mass planet from our planetary system is a very common thing, right? So it's actually very logical, very natural to hypothesize, well, if other planetary system can eject Earth mass planet, why can our solar system also do it, right? So why don't we just hypothesize that one or more Earth mass objects also formed in the giant planet region and were scattered out, and eventually they become free floating planets made in our solar system? If that's the case, we need to study the gravitational effect of such a ejected planet or a scattered planet, which in this case, in this talk, we call it the rogue planet. We call it the rogue planet. And its gravitational effect could have affected the Kuiper Belt. Okay, so this is what we care about. So in this scenario, okay, let's get back to the NICE model, the one of the most successful model explaining the outer solar system. But this time, we add one or more Earth mass planet in the giant planet region, right? So it's shown by this dark blue circle, okay? And Neptune's still migrating into this disk. And then the planetesimal or asteroids still get scattered to very highly eccentric orbit. And so is the rogue planet. A rogue planet was also scattered to very large and highly eccentric orbit. And its gravity will start to do things, okay? So what kind of thing it will do? It will tend to lift the perihelion of objects embedded in the scattering disk. Okay, just as this diagram shows. So it will lift this object perihelion from 30 AU, from 30 AU to 60 AU. And that's all you need. That's all you need to explain this population. You don't need a current planet 9, you just need a already gone planet, which was part of our solar system. And after the removal of this planet, because this planet is not stable, you see, its orbit is crossing Neptune's orbit. So there's no way this planet is stable. After its rejection, Sedna or Sedna-like objects basically stop feeling the gravity of this blue planet, and it just left there. So this model can very naturally, if the sun was born with more planets, can very naturally create Sedna and other senoids. Okay, so to demonstrate that, this is probably the most technical figure, but I'll try to explain it in detail. So here I'm just showing you one numerical simulation that fully explain the whole story. Okay, so here we have a Neptune first formed here. So it will first migrating into this planetesimal disk, right? So the planetesimal disk is here, the black dots. And besides Neptune, we also add a rogue planet here. Okay, and let's play the movie. And you can see that this is Q and this is A, right? So the rogue planet can very quickly detach a bunch of objects to very high perihelion. It's a very natural process, and until its ejection, until it's gone. And if you match this model with our current understanding of the outer solar system, you can see all the crosses are real discovered objects, and the blue dots are particles, are the objects produced by the model. And you can see it basically covers the entire parameter space of all the discovered objects. So we can say, well, this is probably a very promising model, but maybe you wonder, okay, where can we find this rogue planet, right? I can tell you, there is no way you can find this rogue planet, because if it's true, it was ejected 4 billion years ago, okay? And the sun is in the galaxy, and there are so many stars nearby, so you can never trace back where this planet was. You can never detect this planet at the current era. There's just no way. So if that's the case, well, how do we actually verify, or most importantly, falsify this hypothesis? We know that the falsifiability is actually one of the greatest quantity, one of the most important quantity of a scientific theory. right? If you propose something that cannot be falsified, that's actually not science. That's more like a religion. But a scientific theory need falsifiability. So we need to see what kind of thing can be used to falsify this hypothesis, right? Like I just explained, the rogue planet will lift the perihelion of a Sedna-like object, just like this. But I intentionally like hiding a fact, which is this only happened when the rogue planet's apsidoline is close to the asteroid's apsidoline. So what is apsidoline? Apsidoline is just the line connect the perihelion to aphelion. So this long line is just called apsidoline, right? So only if this line and this orange line are on top of each other, are aligned, its perihelion can be lifted. Let's say if there is an orbit that looks like this, right? It never gets lifted. So we can then do some exercise, right? So if all the sphenoids were created by the rogue planet, and the rogue planet only lift the perihelion of asteroids close to its apsidoline, then we can test this. We can say that the apsidoline of all the sphenoids must have clustered 4 billion years ago. Right? So are you guys with me? Yeah. So if it was truly created by the rogue planet, so their apsidoline must align 4 billion years ago. And that's verifiable, that's falsifiable, because we can do a numerical integration. Okay, so this is their current orbit of the 4 sphenoids. Okay, let's stop here. This is the current orbit, 0 billion years ago, so this is the current era. And now we're going to integrate their orbit back to 4 billion years ago and see what happened. Okay, so let's go. So let's do the time magic, everything rewind back to 4 billion years ago. And you can see that their orbit actually are very close to each other. 4.2 billion years ago. That's like the largest clustering. And this is my honest reaction when first discovering this phenomenon back in 2023 when I was like writing my PhD thesis. I was like, well, is this really true? I can't not believe it myself. But at least for now, it holds for the 4 sphenoids, and we know they are the most stable solar system objects out there. Okay, we can also like do more like technical analysis, but I don't think this is that interesting. But you can see that this red line denotes the strongest cluster, basically. So the strongest cluster happened at minus 4.2 billion years, and the p-value, or like the statistical significance, is like 2.4%. Okay, so why? So the rogue planet can do that, but how exactly? Because I have the simulation, so I can just plot the same simulation on another coordinates. So here the y-axis is now this angle called pomega, which denotes the orientation of the apsidoline, right? And the x-axis here is the perihelion, and you can see that this is rogue planet's apsidoline, and you can see that it builds a mountain along its own orbit, right? It's very clear. And there is a very strong cluster in the pomega space, which signify the alignment of their orbit in physical space. 4 billion years ago. Yeah, 4 billion years ago is very important. And okay, so this is their orbit, their apsidoline like 4 billion years ago, and this is their apsidoline now. So unfortunately, for most of the sphenoids, because of they all have their orbit will stellar process due to the gravitational effect of the giant planets. They all have like different precession rate. So this differential precession will mess things up. Well, basically, like it's kind of like a shuffle, right? It was ordered 4 billion years ago, but after some rounds of shuffle, it become uniformized, homogenized here. Okay, so yeah, so that's the rogue planet can create this. And what can future surveys tell us? Well, there are two major, I would say there are two major telescope in this arena. So the one is LSST, which is going to be produce data like late November this year. So this is one of the greatest telescope for solar system science. I will show you why. And another very powerful telescope is of course the Subaru Telescope. So Subaru Telescope can go very, very deep, and LSST can cover a very wide range of sky. And you can see that from this animation, which is not produced by me, but the LSST team. So you can see this is a star, that's a galaxy, and the moving stuff is an asteroid, okay? And every few nights, LSST will take picture, okay? And they will connect the picture and make this kind of movie and identify moving objects and their asteroids, right? And the LSST will do this over and over again for basically all southern sky. And look at how many asteroids this telescope is going to discover in the next following year. It's amazing. And that's just a very small chunk of the sky. So yeah, so that's how powerful this telescope is going to be, and it's going to basically revolutionize the whole field, including our understanding towards the outer solar system. And another future test, which is actually, this is a Subaru survey that, a Subaru proposal, like led by me, because we realized, well, LSST is good at discovering like near-Earth asteroids and main belt asteroid, but for xenoids, which are very, very far away, it's not going to, it's going to discover like 5 or so more, but Subaru can basically do very similar thing given enough time. So here I'm just, in my proposal, I propose another Subaru survey, which is called Fossil SSR. We tend to like match the discovery number of LSST, which is 3.5 xenoids. If we go this deep and then cover this large, like 27 square degree of sky, we, in theory, if my model is correct, we are going to discover 3 or 4 xenoids in the next few years. Okay, so yeah, the future is very promising. So yeah, thank you so much for your attention. Yeah, that's the end of my slides. Thank you.
We are trying to do a new recording system, so can you hold it? Yeah.
One question. You talk about the influence of passing stars and their possible impact. During a 4 billion or plus period of time, Earth crossed a pretty massive amount. Earth, I should not say Earth, I should say the solar system crossed a pretty massive amount of other stars in its burst clusters. Then after, I don't have the exact statistics about the frequency, but it's probably dozens or hundreds of times.
Yeah.
So is the cumulative impact of those meetings potentially more significant than the impact of a one or several rogue planets being ejected from the solar system at the beginning of the story of the at the beginning of its story. Yeah.
Yeah, that's a fantastic question. So yeah, indeed, as you just said, in the past 4 billion years or so, the solar system is going to have multiple encounter with passing star, right? But if we work out the actual frequency and distance, we realize that given our current solar neighborhood environment, the passing star, even with multiple passing stars with their collective effect, it's very, very hard to explain the formation of senoids. This has been inspected by previous researchers. So the reason why this kind of passing star works, it is believed that the sun was actually formed in a much denser stellar environment, like in a star cluster. Okay, so in that case, the frequency of getting one passing star like this is high, much higher than today's environment, right? So in this case, you can actually create senoids using passing star. But with current environment, it's the chance is basically negligible, I would say. Yeah.
And we have
Yeah.
and we have almost no chance at all to know what were the condition of our birth cluster
No,
4.5 billion years ago.
that's also a great question. So in the stellar flyby hypothesis, it's actually, you can constrain the size of the cluster. It has been done in the Adams 2010 annual review paper. So the logic is they use like, I believe 3 things to constrain the size of the cluster. So one is you need to create Sena. And second is relative to the supernova density in our solar neighborhood, which is very complicated. I don't want to go too deep into this, but they constrain using like 3 different condition. They can constrain the size of the birth cluster to, I think the number is like 1,000 star, something like that. Yeah, but that's under the assumption that senoids are produced by the passing star. Yeah.
Other questions? Yes.
Maybe a follow-up on this. So in this stellar flyby, would this also affect the planets, the gas giants in the solar system?
Yeah, that's a great question. So as you can see here, so actually this flyby is peri-astron, so the closest approach to the sun is actually 200 AU. So at 200 AU, it will have a very negligible effect on even the outermost planet Neptune. So in this case, not. Actually, this is also used as a constraint to like constrain the size of the cluster, because if the cluster is too dense, it's more likely to strip away Neptune or the outermost planet. So the comfortable range is like 200 to 500 AU flyby. Yeah.
Thank you.
Other questions? Yes.
I may have missed it, but in your simulation, how large is this potential rogue planet? Is it like a rogue gas giant?
Oh yeah,
like a
I
rogue
forgot to mention
super
it.
Earth?
Yeah, so here in my simulation, I assume the rogue planet is 2 Earth mass. Okay, so that's like the typical mass for super Earth in like exoplanet system, and the reason it cannot be too large is if this is a gas giant, because this rogue planet is also interacting with Neptune, right? If it's a gas giant, it will like perturb Neptune's orbit too much, and that's not wanted. If it's too small, if it's a Mars size, then you don't really build this mountain. Yeah, you don't really create this kind of structure. So the suitable range is like Earth mass.
I think it might like enter that realm of possibilities. But is there any chance that we might be able to constrain like how big this rogue planet actually was, or like how many of them there possibly were?
Yeah, it is possible to constrain that. I would say yes. That depends on because now I'm using the primordial clustering to like test this hypothesis, right? If there is only one clustered angle, if all the primordial senoids are like pointing in that direction, then most likely there was only one rogue planet, right? That doesn't mean that is not to say the sun only formed with one planet, because maybe only one planet got placed on this type of orbit. Maybe a lot of them just got ejected directly, right? Maybe only one leave a observable trace in the solar system. So, and that hasn't been worked out, but that's a great question. Yeah.
One or two questions.
Can you actually? So I have a question about objects that are not sednoids. Can you do similar back integrations for these, like elliptical but not sednoids per se, and expect these kind of primordial alignments?
It is. I actually, so for, you can see that there is another population which I call the detached ETNO. They're color blue here. They have perihelion distance between 40 to 60. Unfortunately, their orbital evolutions are chaotic. So which means with current orbital uncertainty, we cannot concretely say, we cannot pin down their primordial orbit back to 4.5 billion years ago because of chaotic dynamics. I already did integration for all of them, and none of them have regular or non-chaotic evolutions.
I see. Okay, and when you say the other, like the orbits of sednoids are not chaotic, are you back integrating the precession at 4.2 billion?
Yeah, I back integrate. Yeah, their main evolution is dominated by precession. Yeah.
I see. Okay, thank you.
Okay, maybe one last question. Oh yes.
How many pages was your doctoral degree thesis?
How many? So sorry, can you say that again?
How many?
How many pages was your PhD?
Oh, how many? I think it was like a 250 or maybe 300 page thesis. Yeah.
Can we take that question quickly?
Oh yeah. Sorry.
More for future.
Sorry, you can just hold it.
Yes, so my question is, you explained that we have only two observatory looking at the Kuiper Belt for looking for senoids and other objects, but they are mostly located on Earth. Do we have space-based telescopes for this, similar to Hubble or James Webb, that also look for the objects in Kuiper Belt right now?
So you mean, do we have a powerful space telescope to discover them?
Yeah, to look for Kuiper Belt specifically.
Yeah, unfortunately, no, because all the space-based telescope now have very limited field of view, which means they can only image a very small patch of sky. But to discover even one object, we need to image a very large chunk of sky. So currently, no, but I heard a Roman space telescope might do a more wide survey on all sky, northern sky. So yeah,
Also, a lot of the space-based are these objects are too close to us to observe because the space-based are actually looking a bit far.
Okay, thank you.
Okay, thank you so much. So can you stay a little here?
yeah.